Good morning, good afternoon, good evening, depending on when you're watching this. It's your boy Mr. Malachi, and in this video we're going to be going through all the Euclidean geometry proofs that you do need to know for your tests and exams. And yeah, I'm just going to be going through them. Some of them you can extend them to fit whatever picture you have there, but these are the general proofs. There is a couple of ways that you can prove these. I'll only be showing one method. So if your teacher showed you another different method, that's also fine. It's quite fine for you to apply whatever method they've used or to take upon whatever method I'll be going through. So without any waste of time, let's jump right into it. So the first theorem that you would have worked with, theorem 1, is this whole idea of a line from center that is perpendicular to a chord. Right, let me draw it. There's my circle. Maybe draw it a little bit better. There we go. And what this law says is if you have a line and this line from the center is perpendicular to a chord, then that line will bisect that chord. Right? So if this is a O, this is a A, this is a B, and this is a C, what we are required to prove, RTP, required to prove, is that AC is equal to BC. That's what we're required to prove, right? Basically, it says if there's a line from center and it's perpendicular to the chord, then it will bisect that chord. So what that does mean, what does that mean? It means these two sides there are going to be equal to each other. So let's prove that using our laws of mathematics that we know. So the first thing that we're going to do is we're going to construct that line there, the OA line, and we're going to construct that line there, the OB line. So let me write these because you have to write these out. You have to construct line OA and OB. This is a mark, guys, so it is very important that you actually write it down and that you're drawing it on your diagram, right? Then once I've constructed that, then I have these two triangles that I have in front of me. There's this one here, the red triangle, and then there's this one here, which is the green triangle, right? So in those two triangles, all that I'm trying to prove is that those two triangles are actually congruent to each other. If they're congruent, then these sides are going to be equal to each other. So what do I state first? I know that OA is the same as OB. That line here is going to be the same as this line there. And why am I saying it's the same? Because those are both radii. So I've stated the first thing that I need. The second thing that I need to prove congruency is that I will state that this line OC is the same or is common in both triangles. So line OC is common. Then I need one last thing to prove this. So I'm going to state one last thing, and that is this angle here. So angle OCA is going to be equal to angle OCB because they're both equal to 90 degrees. This is a given statement, right? And then with all those three statements stated, then I can conclude, therefore, triangle OCA is congruent to triangle OCB. Consistency is very important. So it has to start OCA, and the next one needs to follow the same thing, OCB. And I'm saying they're congruent. Why? Because this is right angle, hypotenuse, and one of the side is the same. So RHS. And since those are congruent, remember what congruent means? It means this red triangle and this green triangle are exactly the same. If those are exactly the same, then it goes to conclude, or it goes to tell me that actually AC and BC are equal. So this then follows that AC is going to be equal to BC. And what is my reason? This is a line from center perpendicular to chord. And there we go. So this is proof for theorem number 1. Let's jump into theorem number 2. Alright, so theorem 2 looks like this. The theorem, what it says the angle at the center is equal to twice the angle at circumference. So pictorially, it's saying that this angle here, if I times it by 2, I would get the angle at the center. So that's what this theorem is saying. So what am I required to prove? I'm required to prove that angle AC, or rather AOC, is equal to twice of angle B. That's what I'm required to prove. So let's do some constructions. Again, we do need to construct. So the first thing I'm going to construct is this line there. I'm going to extend it a little bit past O, right? So here, construct, and the line that I want to construct is the line BP past O. It has to go past O, right? The line BP that goes past O. And once I've constructed that, then let me label this guy O1, and let me label this guy O2. And let me label the guy at the top B1, and let me label this guy B2. Then what you will find in this green triangle here, there are 2 triangles there, this green one, and then we have another triangle, which is this pink one here, or a red one if you will. So those are the 2 triangles I'll be looking at, right? Let's start with the green triangle. So in that green triangle, if B1, so I will say let B1 equal to X. If B1 is X, then A, the guy at the corner, A will also be equal to X. And you're sitting there asking, Mr. Malachi, where are you getting that? I'm saying that this will be the same as that angle up here. And where am I getting that from? If you notice, this is a line from the center to the circumference, so that's a radius, and this is also a radius. And so the angles inside of those guys, since these 2 lines are the same, the angles inside of those 2 guys are going to be equal. And my reason here is angles opposite equal sides. So that's why I'm saying those guys are the same, right? Then I've asserted that A will also be X. And so O1 outside, angle O1, this exterior angle there, is going to be equal to the 2 interior angles, the sum of the 2 interior opposite angles. So it's going to be equal to B1 plus A. And this is just an X plus an X, which is a 2X. Right? So that's what O1 is there. And what am I using for this? What is my reason for this? My reason for this is an exterior angles of a triangle. So exterior angles of a triangle. All right, so I'm done with the green triangle. Now I need to go into the pink triangle. And in the pink triangle, I'm going to call B2 up there. And I'm going to make that equal to a Y. So if B2 is a Y, I'm going to let B2 equal to a Y. Then C, the one at the corner, will therefore also be Y. And my reason is the same as this one here, which says angles opposite equal sides. Right? And if that's Y, then it goes to show, or it goes to follow the same logic, that O2 there will therefore be equal to the B2, the guy at the top, this one here, plus the C. And this is just Y plus a Y, which is a 2Y. And what am I using this? I'm using exterior angles of a triangle. And then at this point, you should see something pop up. So what I'm going to do is I'm going to take O1 and I'm going to add it with O2. So let's take O1 and add it with O2. And then we're going to make a new equation. O1 plus O2 is equal to a 2x plus a 2y. So that's what I have for O1 and O2. And that's this total angle there. Maybe let me label it. That's AOC, angle AOC. That's that angle there, right? And what is the angle at the top there? The angle at the top there, the angle of B, the total angle of that guy is equal to B1 plus a B2, right? The total angle around that guy will just be this B1 and the B2. So if I add those, B1 was an X, B2 was a Y. So I get an X plus a Y. Then what you will notice is that in this OAC, if in that equation I just factor out the 2, I'll have an X plus a Y. And what is that X plus a Y? X plus a Y is actually equal to B. I'm getting it from there. And so AOC, we can now conclude, is equal to twice of B. And what is my reason for this? This is line, not line from center, rather. Angle at center equal twice angle at circum. And there we go. We're done with proof number 2. All right, let me just quickly run you through this. So the first thing that you need to do is obviously construct. You're constructing BP, this line here all the way to P, and it has to pass through the center, which is O, right? And then from there, you can let B1, the B this side, equal to X. And then you work with that triangle there, and you'll end up with what O1 is, which is equal to 2X. Then in the pink triangle, you're going to let B2 equal to Y. There's it down there. And so C will also be equal to Y. And so O2 is equal to 2Y. Then this total angle here is just O1 plus O2. And that's how I got this equation there. Then if I factor out 2 in that equation, I just get X plus Y. And that X plus Y is just equal to angle B. And that's how I end up with this guy, right? So for each of these, you do need to give reasons. The only time reasons are applicable is for this guy, opposite angles of equal sides, or angles opposite equal sides. For this guy again, for this exterior angles, these the reasons are very, very important. And lastly, this reason here for making your conclusion. All right, I hope that makes sense, guys. You can pause the video, rewind if you really want to follow through what is happening there. But I'm going to move on to the next theorem. So theorem number 3 is the one about angles in the semicircle. So angles in a semicircle, those add up to 90 degrees, or those subtend 90 degrees. So we won't do that one because it follows from this theorem, which is theorem number 2. Let's rather do theorem number 4. So theorem 4, what theorem is this one? All right, so this one is quite interesting. It's I won't say my favorite. It's close. It's my second favorite, right? So what this one is saying is that opposite angles of a cyclic quad, what do those angles do? If I have a B here, the B and the D, the guys that are opposite to each other, they're going to add up to 180 degrees. And again, the A there and the C there are going to add up to 180 degrees. So what I'm required to prove is that B and D are adding up to 180, right? Again, I need to do constructions. So let's construct. And what we're going to construct is we have a center here, which is O. We're going to construct a line OA. I'm going to put a dotted line. And we're going to construct another line OC. So we're going to construct OA and OC, right? Then we're going to use the previous law to say that this angle here, let's call it O1 and call this O2. So O1 is going to be equal to twice of B. And what am I using here? I'm using angle at center equal twice angle at circum. That's the reason that I'm using there. So since O1 equals to twice of B2, O2 at the top is equal to twice of D. So it's twice of D. And again, same reason. Angle at center equal twice angle at circum. Right? So now I've stated those two things. Then what I notice is happening here is that I have a revolution. So if I have a revolution, that means that O1 plus O2 are going to add to 360 degrees, right? And what am I using for this? This is angles around a point. All right, point is PT. So that's my reason there. And all I need to do is take this guy, replace him for O1 there. Take this guy, replace him for O2, and just rearrange my equations. So I have 2b there plus 2d there is equal to 360. Then when you rearrange, you take out the 2 there, b plus d is equal to 360. And if you divide by 2 there and you divide by 2 there, you will see that actually b plus d is going to give me 180. And what is my reason here? The reason here is these are opposite angles of a cyclic quad. And there we go. So this one is quite straightforward. There isn't much of brain activity that needs to happen for this one. You just need to remember that you're using actually law number or theorem number 2 to state that O1 this side is equal to twice of that guy there, and you're stating that O2 that side is equal to twice of the D there. And then once you've stated that, you can do angles around a point where you're saying O1 plus O2 will give me 360, angles around a point, and then from that you can just substitute and you'll find your equation, this final equation, and you just put in your reason there. So this is theorem number 4. Let's move on to the next one. All right, let's look at theorem number 6. I've skipped the proof for theorem number 5 because again that one follows from the theorem number 4 that we did, and that one is about the exterior angle of a cyclic quad. So if you can already tell that the interior angles of a cyclic quad, the opposite ones, they add up to 180, so the exterior one will be equal to the interior opposite one. So that one I wouldn't do a proof for it because again it follows from theorem number 4, and the ones I'm focusing on are really the ones that test that your examiners really like to test, right? If you check in almost every past paper, there's either going to be theorem number 6 there, theorem number 1 there, theorem number 4 there, or theorem number 9 there. They also like theorem number 8, so I'll go through that one. So going back to this one, what this one says is that these angles in the same segment are equal. So what does that mean? It means that A at the top and B at the top, since they're in the same segment, those angles are going to be equal. And similarly, the C at the bottom and the D at the bottom are also going to be equal to each other. But how do we prove this? So I already written my required to prove there. We're required to prove that A and B are equal to each other. So what we need to construct is this line here, the OC line, and we need to construct this line there. So let's construct. So take note, guys, I am writing what I'm constructing, but I'm also actually constructing it. So I'm constructing line OC and line OD. Right? Then once I have those, then I can start to see something. Let's call this O1, this side, right? Let's call that O1. What I'm noticing is that O1, using theorem number 4, O1 there is equal to twice of A. So twice of angle A. And what is my reason for this? It's angle at center equal twice angle at circum. That's your reason for saying that, right? And then I'm going to assert again that the same O1, if you're looking at B, it's also equal to twice of B. So O1 is equal to twice of B. Same reason. Angle at center equal twice angle at circum. So what's nice about these proofs is that once we've proven something, we can grab it and use it to prove the other things, right? So since these are both equal to O1, then it would go to reason that I can make them equal to each other. So 2 of A and 2 of B are equal to each other. I just equate it there, it does not need a reason. So if I divide by 2 there and I divide by 2, this then tells me that angle A is equal to angle B. And my reason for saying this, these are angles in same segment. And there we go. So at this point, guys, I hope you are seeing these and you're finding these quite interesting and they're becoming second nature to you. You're looking at it and you're like, no, I don't have to cram this. I can actually just understand it now, study it before my test and exams, and I can just apply it, right? How I went through my high school is that I would just cram this. They never used to make sense to me. But now in retrospect, looking back, I'm like, no, these just need to make sense to you. And once they do, then you can always remember it forever. Like right now, I'm teaching it and I don't even need to check my notes because I remember it. So let's talk about theorem number 8. I'm skipping theorem number 7. Theorem number 7 is the one about a radius and a tangent being perpendicular to each other. So that is an axiom. An axiom means we just accept it. It's true. So we don't have to prove it, right? Let's do theorem number 8 instead. And this one says tangents. It speaks about tangents from the same point. So how does that look pictorially? Alrighty, so that's how our picture looks. So we have this tangent that goes through the center, well, not the center, the circle, right? At point A, it's a tangent, it goes to P, and this is also a tangent that goes through, I wouldn't say through, but it goes past the circle at point B to a point P out there. And what we also have is we have the center here, right? And what the question is asking us, these lines here, what the question is asking us, let me just move this line back. All right, as I was saying, we are required to prove that line AP is the same as line BP, right? So right now we don't know that these are equal. We are required to prove that they are equal, right? So let's start with some constructions. In almost every single proof, there is constructions that you need to do. So the construction here is that we're gonna construct this line, which is the OA line, and we're gonna construct this line, which is the OB line. But not just that, and we're gonna construct this other line that cuts right in the middle all the way to P. So we're gonna construct OA and OB and OP. So those are my constructions, the lines that I'll be constructing onto the picture, right? And then now we have those lines. Again, we're looking at two different triangles here. We have this pink one here, right? And we have the green one at the top. So again, you're seeing two triangles. It has to do with some congruency of some sort that we need to apply here. All right, the first thing that I notice in the triangle at the top, the green triangle, is that if this is a radius OA, and if this is a tangent AP, then that angle there has to be 90 degrees. Where am I taking this from? I'm taking this from theorem number 7, which says if there's a radius and a tangent, the radius will always be perpendicular to the tangent, right? So I can state it that's saying OA is, actually I'm talking about the angle A. So this should read OAP is equal to 90 degrees. And why am I saying this? This is a red that is perpendicular to a tangent. And I can state the same thing in this other triangle, right? And what is that equal to? This is the same as OBP, which is also equal to 90 degrees. Same reason, red perpendicular to 10. So what does this tell me? It tells me that actually OAP is therefore equal to OBP. They're both equal to 90 degrees, right? So if they're both equal to 90 degrees, they both have to be equal to each other. So that's my first statement. Now I need another statement, something else that is the same. So I notice that this line here, OP, is common. So OP is common, or common length, or common line, something. So I'm gonna just write it's common. Then now we have that. We just need one last thing that is the same between these two triangles. Anything? You noticing something? Ooh, you should be screaming or shouting or like just letting me know that actually OA and OB are also the same. OA is the same as OB. And why? Because they're both radii. They're both a radius. So two radiuses that are equal to each other is just radii. That's your reason for that. then I can conclude that therefore triangle POA, the one at the top, is congruent to triangle POB. And my reason for that is, again, the same reason as I had a right angle, I had a hypotenuse that is the same, and I had one more side that is the same. So that's my reason of saying those guys are congruent to each other. So if those guys are congruent to each other, then it goes to say that these two angles, or these two sides here, are going to be equal to each other. So AP is going to be equal to BP. My reason for this, these are tangents from same point. And there we go. So this is theorem number 7. I'm going to do just one last theorem and we're going to call it a day. So let's do the next one. Alright, so for this last one, we're given this picture that you see in front of you. It's theorem number 9, and this one is my favorite. And what it says is that tangents, the angle that a tangent forms with a chord. So this angle here, that this tangent at the bottom is forming with this chord at the top, is going to be equal to where the chord subtends. So that chord subtends at B. So this angle here at B is going to be the same as C2. That's what we're required to prove. This also follows that C1 then will be the same as A up there. So I'm just going to prove one of them, but as soon as you can prove one of them, you can extend it to the other one, right? So what are we required to prove? I've already written it there, that B is the same as C2. What we need to construct though is we need to construct this line here that goes all the way down there. So we need to construct PC that goes through the center. This is the center O, through O, or past O. Through O, past O, same thing, right? Then once I've constructed that, there's one more line I do need to construct. I need to construct this other dotted line there, and that line is called the PB line. So now that I've constructed that, let's work with those triangles. So one thing I'm noticing, right? This total angle there, I hope you guys are seeing that total angle there, not just the C2, but the total angle there will be 90 degrees. Where am I getting that it's 90 degrees? I'm getting it from theorem number 7, which says if there's a radius, O, all the way to C is a radius, and there's a tangent, those guys are always going to make a 90 degree. So let me state that first. I'm going to state that P C D is equal to 90 degrees, and my reason here is a red perpendicular to 10. Right, so I've stated that guy. Then another thing I need to state is that within this triangle here, the green triangle, what I'm noticing is that since this guy is a diameter, any diameter subtends 90 degrees onto your circumference. So it tells me that this angle here is going to be 90 degrees. And what rule am I using there? I'm going to say PBC is also 90 degrees, and my reason is angles in a semicircle. Alrighty, so I've stated those two things. Then what I need to state is, what is this angle here? So not the total angle, just the angle between ACO or ACP. So that angle ACP is going to be 90 minus the C2. Right? And I don't need a reason for that, because I'm saying if this total angle is 90, then definitely the top one will be 90 minus the bottom. Total minus the bottom, right? Then another thing that I'm going to state is that I want this angle here, the one outside. And then for that one, I'm going to say angle PBA. PBA is also 90 minus, but that one is minus B. So, oh wait. Yeah, it's 90 minus B, right? So that's that angle there. So if those are set up, another thing that I should notice, this is quite hard to see it, so let me highlight it for you, is that if I'm coming from this point and this point here, this goes there, right? But those 2 points also go there. So what does this tell me? It tells me that those guys are the same. And why am I using that? Because those guys are angles in the same segment. So it's telling me that this guy here, which is ACP, is the same as PBA. So those guys are the same. And why? Because these are angles in the same segment. Same segment. So I've stated those two things. And what you will notice is that we have equation 1 here, we have equation 2 there, and I've just linked equation 1 and equation 2. I'm saying they're equal to each other. So all I can do is take this right hand side and this right hand side and make those equal to each other. I'm going to equate those. So 90 minus C2 is equal to 90 minus B. And if these 90s subtract, if the C2 comes this side, the B goes to the other side, you will finally get that B is equal to C2. And this is what we are required to prove. There we go. And my reason for this is the 10 chord theorem. And there we go. So on that note, guys, I hope this makes sense. This is all the proofs that you do need for Euclidean geometry. In the next video, I think I will do the proofs that you need for what do you call this, sequence and series. There's some proofs that you do need for, there's a couple of proofs in mathematics that pop up here and there. And so in the next video, I will focus on dealing with those type of proofs. I hope this was insightful, that you got something out of this video. On that note, that's it from my side. Bye.